Alrighty, good morning everybody. Welcome back to Galois Theory. I almost said Math 105.
Hi, Lydia.
Hi, Lydia. You're in Math 105 now. Plan for today we're actually going to get into what do field extensions have in common with polynomials specifically. And how, given any particular type of field extension, there may or may not be a polynomial that gets associated with it. Leading us to the 10-part theorem, 10-ish part theorem, I didn't actually count it, that I referred to the other day. Got my usual office hours next several days. Homework 5, it's going to be due next Thursday. It's such an exciting homework that it's not even finished being written yet. But plan to do that this afternoon.
It's going to be 2 problems.
Is it going to be 2 problems? No.
1 problem.
Am I?
It's going to be 18 and a half problems.
It's going to be several examples. It's going to be sort of like homework 4. In regard of there's going to be lots of here's a field extension. Give me its minimal polynomial. We're going to get into it today. So, with that in mind, how are you doing? Hold up okay? Groovy. All right. Why do atheists not enjoy working with exponential equations?
He really wants you to call on him.
Parker?
Because they don't believe in a higher power.
Because they don't believe in higher powers.
I've heard that joke so many times.
That's a good one.
It's a good
So, start off with, last time we talked about what it means if you have a ring and then in these sort of square brackets you put some element not in the ring. And we said essentially it is the ring of polynomials in A with coefficients from R. So in other words, it's basically the set of all elements in the form R sub n a to the nth power plus ... plus R sub 1a plus R naught. So for instance, when we did this with square root of 2, we said that we get like q adjoins square root of 2, for instance. We said you have polynomials that are of the form a plus b square root of 2 plus c square root of 2 squared plus ... But that's simplified down to just being things of the form a plus b square root of 2. Because once you take square root of 2 and you square it, it becomes rational again. So any polynomial of terms of square root of 2 over the rationals will end up simplifying down to just being something of the form a plus b square root of 2, where a and b are some rational numbers. And so we talked about that towards the end of class last time. Today we're going to get into what happens if instead of square brackets, you get the curly ones.
Curly brackets.
Meaning parentheses.
Yes, because those are curly brackets.
Shut up. So, with that in mind, turns out the main difference is this thing has to always be a ring, but it's not guaranteed to be a field when you have it with parentheses instead of the square brackets. It's guaranteed to be a field. Here's how it's defined. We're going to let K be a subfield of L on page 2 in the packet. And S is going to be some subset of L. Then we're going to define K of S is the smallest, or actually no, well, we're not defining it this way, it just turns out to be this way. Then K of S is going to be defined to be the intersection of all fields, all subfields of L containing both every element in K and every element in S. So in other words, containing the union of the two sets. And in that case, we say that this K of S is going to be called the subfield of L, iterated over K by S. That looks really fancy, but basically think that except you have polynomials and then you also toss in everything you need in order to make it a field and not just strictly a ring. So for instance, let's say we wanted to do Q adjoined square root of 3 with these parentheses. So in this case, whenever you just have your S has a single element in it, and usually we're going to be looking in cases where S has either one or a small number of elements. So S in this case would be set containing square root of 3. That wasn't supposed to happen. By definition, this is going to be the intersection of all subfields of, I don't know, what field do you want to pick that Q and square root of 3 both lie in?
C.
C? C works. You could have said R. This is going to come out to be the exact same field in any case. Containing Q and square root of 3. So what would that look like? If you wanted to look at what has to be contained in all possible fields that include all the rational numbers and that also include square root of 3, what would the elements look like? What would have to be contained in any field containing Q and square root of 3? Andrew?
At least anything of the form a plus b squared of 3 where
Anything that's of the form a plus b square root of 3, where a and b are, what did you say a and b like?
rationals.
Are rationals, would certainly have to include that. Why? Because if you include square root of 3, in order to be a field, you have to be closed under multiplication. So if you include everything in Q and square root of 3, you have to include anything of the form b square root of 3, where b is rational. You also have to be able to add that to any just strictly rational number. Why? Because if it's a field, it has to be closed under addition. So if b, anything of the form a is in your field, and anything of the form b root 3 is in your field, the sum would necessarily have to be in the field. So I would say, Andrew, certainly this is going to be a subset of.
Subfield.
Say what?
Subfield, not subset.
No, subset of Q of square root of 3. The question is this itself a field? Meaning or do we need to throw in more elements so that we get a field? You're right, it is a subfield, but that's what we need to prove that. So here's my question. If this is a field, then we're done, because that's any field containing these things has to include everything in this set. And if this set is itself a field, then, well, clearly this would be the intersection of all fields. But if this isn't a field, we might need to add in some more elements to make it one. So let me ask you this. Is this set closed under addition?
Yes.
Is it closed under subtraction?
Yes.
Is it closed under multiplication?
Yes.
So by the sub-ring test from Math 410, we know that this is at least a ring. Is it a field?
We can generate inverses the same way we did with square root of 2.
Well, let's see. If we take some element in here and try and take its multiplicative inverse, do we get something that necessarily lies in the field? So let's take 1 over, I don't know, a plus b square root of 3. See, can we write something like this in this form? Assuming a and b can't both be 0. 0 doesn't need multiplicative numbers. Anyways?
A divided by a squared minus 3b squared plus minus b root 3 divided by a squared minus b squared. 3b squared.
How on earth did you get that?
Based on what we did the other day.
Okay, how can we arrive at such a result?
Multiply.
Matthew?
Are you multiply by the conjugate?
Yeah, let's multiply top and bottom by conjugate.
Oh boy, I'm glad they can call it the conjugate. That's nice.
Oh yeah. Well, conjugate's nice for other reasons. Which will give us a minus b root 3 over a squared plus ab root 3 minus ab root 3 minus 3b squared, which is equal to, lo and behold, a over a squared minus 3b squared plus square root of 3, or plus quantity negative b. I think you forgot the negative in one.
I did not. I said minus.
You did? Oh, then I didn't hear you.
False.
And if a and b are rational numbers, is this a rational number?
Yes.
Well, we know a and b are can't both be 0, because I said so. If a squared minus 3b squared is 0, then we would end up with square root of 3 is irrational. Or no, square root of 3 is rational, excuse me. Which we know to not be the case. Which is in this set. So it turns out, yeah, you're absolutely right, Andrew. Turns out that this is the intersection of all subfields of C containing Q and square root of 3 happens to be exactly this set right here. This is, in other words, the smallest field that contains both all of Q and the number square root of 3. Any questions or comments relating to that? Emily Rose?
How do you know that the intersection of all the subfields containing Q and square root of 3, I mean it is, but in a more general case, I guess, how do you know that that's also a field
Well, we just proved it's a field.
in this case?
How do we know that this thing is a field in general? You could write, actually, one more problem. That would be a good one more problem.
Start thinking about it now.
And
Guess we can get started.
it's not actually that hard, but I'm not going to answer that question for reasons that may make themselves apparent.
In homework 6, I hope.
Quick, let's start with solving it right now.
Ellen?
So what about because R is a field.
Yeah.
And it contains all of Q and the square root of 3.
So what would you get if you took that?
That's just R.
Yeah.
Yeah.
But R isn't the intersection of all subfields of C containing Q and square root of 3.
Oh, okay.
It happens to be one of these subfields of C that
Okay.
contains these.
Okay.
Another one would be the subfield that is Q adjoin root 3 and root 2, right?
That would also be one.
Yeah.
Another would just be literally all complex numbers.
Okay. So it's just the
When we say
smallest.
intersection, we mean smallest.
Yeah.
Wait.
Meaning something that should itself be a subfield of any of these other fields containing Q and square root of 3. So Jonah, that's when you said C cheekily instead of R, for instance, I said, oh, it doesn't, yeah, sure, we can go with C. Because we're taking the intersection of all of them. It doesn't really matter what your L is, other than the fact that at least one such L exists. Because you're just taking the smallest one when you take this sort of subfield of L generated over K by S, and I'm definitely going to totally remember all of that terminology and not just say, oh, the field of Q generated by square root of 3.
So you can, in the case where you have a field out front,
Mhm.
you can just use that as the subfield. So you can say intersection of all subfields of Q
What do you mean?
containing Q and
What do you mean if you have a field out front?
oh no, so you take
Yeah, like if this is already an element in here, so like if S is a subset of K, then this just ends up being K.
Yeah.
Is that what you're asking?
Well, that's what I was getting to, and now it makes sense why that would be true.
Yeah, because if S is a subset of K, then this just ends up being K, and what's the intersection of all subfields of L containing K? It's K.
Yeah.
Since K itself is already one such thing, and so there's no field smaller than K that contains K. Okay? So, at the bottom of the page, just a little bit of notation. If S is a finite set, we often will just write out like, if S finite, we'll often just write out like K of S. Instead of writing K of S, we might just write like K and then in parentheses, like list out all the elements of S. So like alpha 1 through alpha sub n. And we also say that if S only has a single element, then we call it a simple extension.
S is simple.
Exactly. That wasn't tortured at all. Keep in mind, K of S is always going to be a field extension of K. Why? Because it's a field, and K of S necessarily contains K as a subset, or as a subfield. So K of S will always be a field extension of K. And if it happens to just be by one element like this, we call it a simple extension.
I assume this is a spoiler, but all field extensions can be written in this form.
Ooh, you would be incorrect.
Oh.
What if you have like
Hint, replace square root of 3 with, I don't know, E. Then this would not work. If I were to do, for instance, Q of E.
Like we did
but
Q
that
of
is
pi on the other
that
page.
is the form.
Yeah, well, I purposely didn't want to use Q of pi again because that's appearing on the next page.
That is the form, though. That's
Q of E would not be written like this. Because,
no. That form.
oh, for a simple extension, yeah.
Yeah. So the question is,
Are all field extensions simple? Oh, is that right?
right? No, as any set. Can all field extensions be written as a K of S?
I mean, yeah.
Okay.
Well, yeah, because you could just have like S be whatever you want. Because S doesn't itself have to be a field. S can be whatever subset you want.
Yeah.
So you could just have like, if like L itself, you could just say, oh, let L equal S. Then K of S is just going to be your L, and you could do that for any field extension L of K.
Yeah. Okay.
could you have a field extension that couldn't be written like this if you had it be like a simple extension by a non-computable number?
Simple extension. I mean, in theory, it can be written like that for such a thing. In practice, good luck with that, but in theory, you could totally do that. Yeah, it doesn't matter if it's not computable, if it's computable or not. What that only affects is how nasty looking examples are. And if you keep pushing me, Jonah, the homework 5 will include several of them.
You could stick a variable in there and it would be fine.
Oh, sure. Oh, yeah. So, like, if we were to do, for instance, something like that, for instance. We'll be seeing some of that here in a second.
Ooh, okay, it looks like.
So, if you flip the page, I took the three versions of the polynomial rings from the front page and replaced all the square brackets with parentheses.
And
I'll give you one guess as to what this is going to look like. You're correct. It is everything of the form a plus b square root of 2, where a and b are rational. Hey, this thing is a field already, so this thing turns out to be equal to that thing. Oh, look, it's a simple extension. going to equal that? Well, it's not going to equal that. Is that going to equal that? Square bracket version?
I haven't been able to prove it in the 2 seconds I've been working on it.
But I think it will.
You know, I think it should.
I think it will.
We wrote that one out.
Turns out it will, yeah. I'm not going to prove that right now, because we're going to have, our big snazzy theorem is going to prove it for us.
Is that what it's called?
Sure. You know what? We can call it that if you want. Is this a simple field extension?
No.
No.
It's 5.
Wait a minute, wait, no.
Oh, wait.
Wait, wait a minute. What I almost
I
say,
think it would have to be root 6.
whatever it's saying.
That is not equal to root 6.
No, because you don't get the square root of 2. Or,
Yeah.
Yeah, you have like u primes, so.
What?
Surprise! It is a simple extension.
Oh my
Then-
god.
Even though it doesn't look like it, when you write it in that way, you can also write it in this way. And since square root of 2 plus square root of 3 is a
Oh,
single number,
Because
that,
it has to include them both. Yeah, makes sense.
well, what is,
How do you get from there to?
yeah, it's not, I mean, it is clear that, like, that this is going to be a subset of that, because anything that's can be written in here can be written as some sum of something times square root of 2 plus something times square root of 3. What's less obvious is that this is a subset of that.
I mean, so I can see you can get from there to like root 6, but I don't see any you get from there from root 2 or root 3.
Well, let's find out, shall we? So, I will say, so let's write a proof of this real quick. Since square root of 2 plus square root of 3 is, will everybody agree that that's going to be in here?
Yeah. Yes.
Cool. That tells us that this is going to be a subfield, at least, of this. The question is, other way around. Well, let me ask you this. What happens if you take square root of 2 plus square root of 3 and you multiply it by negative square root of 2 plus square root of 3? Lincoln?
You get negative 2 plus 3.
Equals?
Can someone do that for me? I don't remember.
This is
I don't know.
That's not my number. That's not my favorite.
It's 1! So what does that tell us? These things are multiplicative inverses. It's this thing
Has to be.
has to be in there.
Oh.
And then you just add them and divide by 2. Or subtract them and divide by 2, and that'll give you square root of 2 and square root of 3 individually.
Wait, you do what? Divide by 2?
Well,
Oh, you.
let me,
add that,
look,
right.
yeah,
Never mind.
you add this term to that term. Hence, negative square root of 2 plus square root of 3 equals 1 over square root of 2 plus square root of 3 is an element of this guy, q join square root of 2 plus square root of 3. And then you can write square root of 2 as being equal to 1/2 times the sum of these two things which lie in this field. Nope. That gives you square root of 3. Just had to check that. And then if you subtract, okay, and then if you subtract and divide by 2, you get square root of 2. Because if you subtract, you just get 2 square root of 2 over 2 is square root of 2. So, square root of 2 and square root of 3 individually are elements in this bugger. So, we get the reverse inclusion. So, q adjoin square root of 2 comma square root of 3 is a subset of q adjoin square root of 2 plus. And that's our proof, that this equals that. And so this is actually a simple field extension. It just doesn't look like it. Because it can be, because there exists some element in R or C or whatever you want to call your bigger field, such that extending Q by that single element gives you this field right here.
So we have a hint at how we might write this out in set notation. We need to add some, when they're not equal, because Q bracket 2 square root 2 plus square root 3 is not the same thing. Is
Is it?
That is a,
Yeah,
that
it
is,
says they're all equivalent. They should all be the same.
so how do you get the inverse? What's the B on the inverse? Or we don't necessarily know yet.
To get what? Like just square root of 2 by itself?
To get negative square root of 2.
To get,
Yeah, because
negative
that's
square root
not-
2 plus square root 3.
I don't know. It might be.
We need another, yeah.
Just remember we needed that extra term.
That we need some extra terms there.
Okay.
Holy cannoli.
Wait, that's more terms than we had.
Well, that makes sense. No,
I
that's
give you
the
the
same
square
amount.
root of 6.
Oh, you're right, that is the same.
Hint, this is four dimensional because we have 4 free variables here. And we know that that is a 4-dimensional extension of Q as well. So the fact that they're equal means that they should both have the same dimension as vector spaces over Q.
Mhm.
So in this case, they both have dimension 4. And it turns out it gets messy, but can you be a little more convinced that somehow you can get just square root of 2 and somehow get square root of 3 out of this?
Oh, yeah.
Because you're right,
Yeah,
without
yeah,
the C and D terms, you can't.
No, yeah, that makes sense how you would eventually get to it. But even so now dealing with something like Q, is it still adjoined or no? There's new words for it.
But there are new words. We'll look at them.
Q with pi, then you might need to add inverse pi.
Yeah, it turns out, it is with pi, doesn't work out that well. You need the set of all elements of the form, a sub n pi to the n plus a sub n minus 1 pi to the n minus 1 plus plus a 1 pi plus a naught plus a sub negative 1 times 1 over pi plus a sub negative 2 times 1 over pi squared plus a sub negative m times 1 over pi to the n. And that is not to that. Because this thing because with the parentheses, this includes 1 over pi, for instance. This does not. 1 over pi is not an element in the polynomial ring. But when we extend it out to a field, we actually get that this is going to be a proper subset of that.
That makes sense considering it wasn't a field to begin with.
So do we know that Q with the square root of 2 plus square root of 3 is a field just because we use the open brackets?
Well, because it's equal to this, and this thing is a field,
Yeah, but
or,
when
or because it's equal to Q of A, and maybe you all will have to prove at some point that Q adjoined anything is going to be a field by somehow.
okay.
What?
Q and
Not,
join.
not normally joined.
This
Right.
this adjoin.
This
This,
time.
this,
Yeah, with the parentheses.
Which
Kind
I
of.
thought we defined it, this was going to be.
Well, we defined it as the intersection of all fields containing Q and.
Yeah, but I was just
A.
questioning because our proof just assumes that the inverse of any elements in Q adjoined square root
Yeah,
of
yeah,
2
yeah,
plus square root
so-
of 3.
Yeah, so we're
we
assuming
haven't
this thing
actually-
itself is a field.
Yeah, but we haven't proved that technically.
Technically, we have not.
Okay.
Correct.
Well,
Just checking.
my question was how did we know that was the smallest, not whether or not it's a field.
Yeah, well, you gave me an idea, so neither.
Well, but if your idea is different than my question, you can answer my question.
I choose not to.
So this is sort of Q bracket pi bracket, not so square bracket, not parentheses.
You gotta get your formal.
Even though that is not a field, you could still form a vector space with it using Q as scalars.
Yes.
I don't know. That seems like, I don't know, I'm just sort of theorizing, but it does have, that would have,
That would be
Infinite-
this would be, you could define this as an infinite dimensional vector space over Q.
I'm just curious, because that ends up being a
The real fun part
Un-
comes.
not simple extension.
The real fun part comes when you try doing something like that, where that is not a vector space over Z. That is what's called a module over Z, which is like vector space where your scalars don't have to be a field; they just have to come from some ring with nice properties.
Oh. I don't know, an integer domain or something?
I just think,
Like an integral domain, perhaps.
I just think
Okay,
it's,
Integral.
I just think it's funny that it can't be written as a simple extension and also has an infinite basis as a vector space.
I mean, this is still a simple extension. It's just not a simple extension that's equal to this thing. Matthew?
So the only like difference basically between these is just like rings and fields.
Essentially, yeah.
Okay.
Yeah, this thing is always a ring, this thing is always a field. If this happens to be a field, then these will be equal, but this need not itself always be a field.
Yeah, and the only difference is just basically the inverses then.
Pretty much. Let's look at a little bit of theory. I've got one little theorem before we get to the big one. I've already forgotten.
Shouldn't the
What?
indexing be the same for the Q?
What are
Q2.
It should be a n and a negative n, right? Because then they wouldn't cancel out if they were not equal.
I mean, they don't have to cancel out. Like you don't, like you.
All of the elements have to have inverses. So they would.
Yeah, but you don't have to have the same number of the degree in the positive direction doesn't have to match the degree in the negative direction.
Oh, because you.
Because you could have like pi squared plus pi plus 1 minus 5 over pi. That would be an element in this field, even though you have go up to pi squared in the positive direction and just pi to the negative 1 in the negative direction.
Yes, but in order to have the inverses of something of the form a n pi to the n, you have to have an element a to the a negative n.
No,
One over
it's
pi.
just,
So
you
you
have to
have
write
to-
it down.
every
all
polynomial has to be able to be written like this, but it's not like there's a set n and m that has to be the case for every polynomial.
Correct. If we replace this n with n, it would still give us the same ring because you could just let some of the terms be 0 on the ends. So if it makes you feel better, you can replace these n's with n's. But it turns out it's the exact same set either way.
Because all we're defining is that it has to be finite. We're not saying how close to 0 it has to be.
Correct.
But it has to have at least one negative term.
Well, it has to have all of them.
It has to have potentially be able to include any of them.
Oh.
So any polynomial, any Laurent polynomial, dare I say, in terms of pi over the rationals has to be in here.
Okay.
I'm sorry, what's a Laurent polynomial?
Take complex analysis.
Parker, what's the?
Big poly,
Pardon,
it-
what does that mean?
it's a polynomial. It's a polynomial that can have negative integer powers as well as positive integer
Oh,
powers.
why didn't you just say that?
Oh.
That's so
It's
easy.
basically an extension of the Laurent series is basically an extension of the Taylor series, right?
Yeah.
Yep.
Well, why didn't you just say that?
Yeah, but we have polynomials
We know what a Taylor series is.
because there's no series here. Why are you getting all serious on me?
Parker, what are we naming the fancy theorem?
What are we naming the fancy theorem?
We're not there yet.
Fancy theorem.
You have time to think about
The
it.
fancy theorem.
We came up with a name like 10 minutes ago.
Snazzy big one?
Snazzy.
Snazzy big theorem.
Yeah,
Okay.
All right, here's little theorem before we get to snazzy big theorem.
Fancy little theorem.
Turns out for any
The SDG.
K of S as defined previously, meaning like 2 pages before this one, K of S is the set of all elements of L. I'm not going to write this out. It's the set of all elements of L that can be expressed as quotients of finite linear combinations of finite products of elements of S.
That's really easy.
Okay.
I'm just going to write this. I'm just going to write it in a symbolic form. It's a set that basically says take a polynomial in your S sub I, divide by another polynomial in your S sub I. That's what K of S is defined to be. F of S sub I and g of s sub I are polynomials in K of the elements of S. And as I was looking at this morning before class, I realized Jonah is going to jump on me if I don't include this. Don't divide by 0.
G of S is not congruent to 0?
It's not identically 0.
Oh,
Oh
shoot.
yeah, that's defined.
Well, I was just wondering if that was what he meant.
No, that means not identically 0. It's not just 0, S1 plus 0, S2 plus 0, S3 plus dot dot dot.
Mhm.
You can have values that you could plug in for the coefficients that would simplify to 0, but it's not just going to be the 0 polynomial is what I mean.
We'll probably use for the SI that you
Yeah.
can plug in.
Basically, think rational functions in terms of the elements of S.
Do the S sub I have to be the same?
Well, they have to.
No, I know, but for the F of S sub I and the G of S sub I, do the S sub I's have to be the same? Like you're plugging in the same.
Yeah.
Okay.
Yeah, you're
So
plugging
S
in
sub
all.
I-
So you're plugging in all of the elements in S into both of these.
But you're plugging them in.
But it could just be the case that depending on your F and G, they may be constant with respect to some of them.
Yes.
Like if we were trying to do like Q square root of 2 square root of 3, for instance, we could have like square root of 2 cubed over 1 plus square root of 2 cubed plus square root of 2 squared divided by 3 plus square root of 2 square root of 3 minus square root of 3 cubed. Like the numerator doesn't involve square root of 3 in any way. You can still call this a polynomial in terms of square root of 2 and square root of 3. It's just constant with respect to square root of 3. Is that what you meant when you said do these have to be the same as sub i's?
Not quite, but I think I'm seeing what is going on.
Okay. Yeah, I guess I'm still not sure what you're asking then.
I think I figured.
I mean, I'm
Okay, well if you're happy then.
Basically, you know, if we take S and then make it an S sub T, is the T incrementing at the same rate for both of them? And the answer would be yes. Right, yeah, exactly.
Yeah. I think.
I'm not going to prove this theorem. The reason being, the theorem requires something we didn't talk about called the field of fractions.
The what?
Field of fractions of a ring.
Can you explain that in
Sure, any ring can be extended into a field.
that makes sense.
Basically, it's like in the same way that the integers can be extended into the rationals by just saying,
you can just,
If we just added like
yeah.
2 inverse, 1/2, 1/3, 1/4, and so on for
it can get more complicated than that because
Then you have
because
to
the
add-
integers are a cyclic group and you don't have to necessarily have a cyclic group to find your ring. So it can get more complicated than that, but essentially that's the idea. It's based on
Is it in the book?
it's a book. Ring of fractions. Alright, I'm gonna get to what do you all call it? Big snazzy theorem?
No, snazzy.
Snazzy big theorem.
Snazzy big theorem.
Pardon me, you call it a behemoth.
It is a behemoth because there's like so many things to prove.
The snazzy behemoth theorem.
Yeah, we're going with that.
What are we going with? Snazzy behemoth theorem?
Yeah.
The snazzy Leviathan theorem.
No, not
That's coming later.
That's later, yeah.
The snazzy Cthulhu theorem.
Oh,
We're just gonna say the snazzy king and yellow.
We're going with snazzy big theorem.
Oh,
Oh, we're really calling it that. Okay.
Yeah, y'all wanted it.
We do want
Okay, well there you go. No, this theorem does not have a name that I'm aware of. The minimal polynomial theorem, maybe. Or let L be a field. Let L field take a subfield. Alpha some element in L. And we're going to talk about what are the two possible things that can happen when we adjoin alpha to K as a field extension. Then, one of two things is going to happen. In the first case, we have alpha is isomorphic to the field of all rational forms of coefficients in K. Or you get that it's not isomorphic to that, in which case there exists a unique, monic, irreducible polynomial, M. Irreducible polynomial M in K of X, the polynomial ring over K, such that with the property, so I'll just say such that for all functions f that are polynomials of x over k, three things have to happen. First, f of alpha equals 0, if and only if m divides f. Second condition, the brackets and the parentheses give you the same thing when you adjoin alpha. And third, the degree of the field extension of k of alpha over k is equal to the degree of m. When I said this was a Leviathan, Cthulhu, etc. of a theorem, I meant it because we have to prove, given any field extension, we either have this thing, we either have that something happens which we have to prove is an isomorphism, which means we need to show something is a one-to-one onto homomorphism, or we can find a polynomial and it's irreducible and it's monic and it's unique and it satisfies something if and only if something else, and it has that these two things are equal. These two rings are equal to each other, and it has that the degree of the field extension is equal to something. And to look at the degree of the field extension, we have to look at a basis, which means looking at something being linearly independent and a space set. That's why I said there's like 10 things to prove here.
What does monic mean?
What does monic mean? Good question. Darn.
Like degree 1.
No, that's linear.
It doesn't have, it's just one power. It's like ax to the I.
No. So monic in this case just means the leading coefficient is 1.
Oh, okay.
Okay.
Because you could probably take that polynomial and multiply it by whatever constant you wanted and get the same result, so it wouldn't be unique then, right?
Exactly, yeah. If we didn't include that condition where put a condition on the leading coefficient, then just take any unit multiple of whatever polynomial you'd get another one satisfying all these things. Exactly. So in order to guarantee uniqueness, you need to restrict something. And that's one way to do it. Alright, good news and bad news. And good news. The good news is we're going to prove this. The bad news is we're going to prove this. And there's a lot to prove. The good news is none of these things are individually that difficult to prove. Before I prove it though, I want to look at a couple examples. This m, by the way, we're going to call the irreducible, the minimal polynomial of alpha, the polynomial that satisfies all these properties. So let's take a look-see. Before we start proving anything, just doing a couple examples. What is the minimal polynomial of square root of 2? So minimal polynomial of square root of 2 over q means we need some polynomial. It has to be leading coefficient 1. It has to be irreducible over q at least. It has to satisfy that if any other polynomial, if square root of 2 you plugged into any other polynomial, you get 0, then m has to divide that polynomial. it also has to have that the degree of that polynomial has to be equal to the degree of the field extension k of square root of 2 over k. So in other words, it has to be a degree 2 polynomial. We've already seen that's 2. So what would be a degree 2 polynomial that if square root of 2 is a root of that polynomial, that if square root of 2 is a root of any rational polynomial, that polynomial is going to have to divide it.
Wait, what?
So in other words, what would be the m corresponding to square root of 2, alpha equals square root of 2 in this case?
I believe you should be able to get like a squared plus 2 squared, not 2 squared, 2.
A squared plus 2. So f of x, I need an f of x equals,
Oh, f of x.
or m of x equals.
Sorry. M of x equals x squared plus 2. That's not degree 2 yet.
That's degree 2.
That's
Yeah, that's x squared. Unfortunately, it doesn't quite work because square root of 2 isn't actually a root of this polynomial. And you need that-
Minus 2.
Ah, x squared minus 2. Square root of 2 is certainly a root of that.
Because the one you had has I root 2, right?
Oh.
It does. He was close. So this is a polynomial, x squared minus 2. It has the right degree, so it satisfies condition 3. It's a little tricky to prove condition 1, but it checks out. It's tricky to prove it directly, but it turns out any rational polynomial with square root of 2 as a root has to be a multiple of x squared minus 2. For similar reasons to how we proved irreducible polynomials of R of degree 2 or 3. And it's going to be the only monic irreducible polynomial that does that. This thing's irreducible over Q. Why? Eisenstein, P equals 2, boom. It's monic, leading coefficient is 1. This is our minimal polynomial for this field extension.
So the I condition comes along easily with anything normal algebra, like when we're dealing with Q.
The I extension? What?
The I condition.
The first subcondition.
Yeah.
I was like, are you talking about the complex numbers now?
No.
Yes, correct.
So what's
Because
the
you always get like these roots can be written out like that.
Speaking of I, though, what would the minimal polynomial for this one be?
Ooh, the rational.
It has to be degree 2, because this is a degree 2 field extension over Q. It's a basis of 1 and I.
x squared plus 1?
X squared plus 1. As we kind of saw in a previous theorem, that if x minus I divides a real polynomial, x plus I will also divide it. Meaning x squared plus 1 would have to divide it. This is kind of a generalization of that result. So, how about this one?
This one needs to be degree 4.
Oh, I was just about to ask. Well, actually finding this one is kind of annoying and hard, but what should the degree of it be? 4? Why?
Because it's a degree 4
Yeah.
field extension.
Because we know this is equal to that. Well, it's equal to the square root of 2 comma square root of 3, which is equal to that. And this is a degree 2 field extension. And this is a degree 2 field extension over that. And as we saw last class, field extension works multiplicatively in that if you have a degree 2 extension over a degree 2 extension, the overall degree of the extension is 2 times 2, or 4. So you're right, it's a degree 4 extension, meaning we should have a degree 4 minimal polynomial. What is the polynomial? I'll give you a hint.
Oh, I have an idea.
Okay, what's your idea?
Is it the expansion? No, never mind. I don't. I have thoughts, but I don't want to speak them.
Emily Rose is too embarrassed.
I know.
Is it just like x squared minus 2 times x squared minus 3?
x squared minus 2 times x squared minus 3. So in other words, just the minimal polynomials multiplied together.
Yeah.
For if you would join square root of 2 and then you would join square root of 3.
Basically what my idea
That would certainly be nice, wouldn't it?
Oh,
Unfortunately, it doesn't quite work. Because it's got to be irreducible, and if it's the product of two degree 2 things, it's not going to be irreducible.
What if we cut out the middleman?
I don't know what that means in this context.
X to the 4 plus 6.
X to the 4th plus 6.
Or minus.
That is, well, x to the 4th plus 6 is not going to have this thing as a root.
Well, no, if we came up with a,
make up a
oh
number.
wait.
This is actually tricky. This is not the sort of thing you can just kind of figure out in your head. Yeah. That Matthew, that was a good guess, and it kind of almost works except for that whole irreducible part. It actually ends up being x to the 4th minus 10x squared plus 1.
How'd you get that?
Which has the same sum of B and C.
Oh yeah.
Oh.
Which you can actually get from playing around with if you take, the hint I was going to give was I was going to tell you what this is to the 4th and what this is squared. And it turns out if you take this thing minus 10 times this thing, you just get 1.
Because there had to be inverses.
Yeah. I don't know. How do we know this thing is irreducible though? Because what?
No, we don't use Einstein.
We could try using Eisenstein. Unfortunately, it wouldn't work because of our
One.
because of this 1 here. It doesn't have any prime factors at all. If this was like x to the 4th minus 10x squared plus 30, then we could use Eisenstein p equals 5, for
What if we
instance.
do reduce mod 3?
Reduce mod 3.
Well, but that doesn't necessarily
one
tell
is
us
gonna
if
get
it's irreducible.
F of 1 is going to be 0.
I don't want to spend too long on this specific example. I think reducing mod 3 will get you there though. You have to play around with it.
I wouldn't.
I think F of 1 will give you 0 in that case.
Minus. Or,
No, because you get x to the 4th minus x squared plus 1, so you get 1 minus 1 plus 1 is 1.
Oh yeah, because that's a 2. X to the 4th plus 2x squared.
yeah.
Wait,
Yeah.
Yeah, it is a 2.
Wait, what?
No, what if you negative
Oh.
x over x
This is x to the 4th minus x squared, so x to the 4th plus 2x
No.
squared
X
plus
squared
1,
is
which would
fine.
give you 1 plus 2 plus
Right,
1 is
Right.
4.
No,
which
he's
is
right.
1.
It's minus 2.
It's minus
It's-
2 because it's
no, it's
negative
plus 2.
10.
Dude, that's giving
Plus 2.
Plus 2 minus 1, whatever
Plus
you
2,
want to call
yeah,
it.
plus 2.
Tomato, tomato.
We'll see.
Alright, how about this one?
Skip.
See the first condition.
Yeah, turns out this one there is no polynomial that'll satisfy it. And the first condition holds instead of the second condition. This thing is actually isomorphic.
Well, because despite all the gobbledygook,
Despite all the comments.
what it's really doing is it's breaking down what happens when they're equal and what happens when they're not equal with square and circle brackets.
What does that like first condition like even mean in like relation to this? Like, how is that?
It means you can't find a polynomial for which that thing is a root. There is no rational polynomial, in other words, whatsoever that has pi as a root.
As their
But what does it mean like for isomorphic or like Q of like what even is the?
What is this?
Yeah.
I guess you would.
Polynomials in Q over polynomials in Q.
If there's roots, then you can make things simpler and not have to make it just an entire thing of fractions.
Basically, it's what you get if you take the field, this isn't a ring anymore, it's a field, but it's a field where you take polynomials divided by other polynomials.
And like it just so happens that that's equal to like all the insane inverses and
Well,
stuff with
think
pi.
about it. If you had like 3 pi squared plus 1, you could map that to 3x squared plus 1.
And that's going to be how we essentially prove it, yes.
So is this just basically saying that transcendental numbers work like variables?
Transcendental numbers, what were those? Pi?
Are transcendental numbers the one where condition 1 holds?
Yeah.
Yeah, this
In
is
the next
talking
packet,
about
By
algebra.
In
definition.
the next
though,
packet, that's how we're going to
It's
actually
literally-
define transcendental numbers.
It's
is
literally.
these are transcendental numbers,
And those
These
are
are-
algebraic.
I need to
These
bring
are-
up-
these are algebraic.
Yeah.
Yes. But this gives us a way to define transcendental and algebraic numbers over an arbitrary field and not just say the rationals.
We can also do stuff like this in terms of cyclic and non-cyclic. Because
Cyclic and not what
well,
being
I'm
cyclic?
getting there. The reason that something like pi ends up being the whole thing, x is just the general form.
Yeah, X is just a form for an indeterminate
Plug in anything.
that doesn't satisfy any special relation.
So the ones that end up falling in case 1 are the ones where you have to go on forever and use up all of the general case to do it. And the opposite of that is it's something cyclic where you do enough powers, eventually you get back to
Yep.
the original.
And now, Isaac, you're thinking in terms of Galois theory. Because that's what we're really going to be doing the second half of the semester with these field extensions. We're going to be talking about what happens if you have some sort of field extension where you start permuting the roots of these minimal polynomials. What sorts of groups do you end up getting? And how can you say that that is somehow isomorphic to some group involving some sort of the corresponding field extension? That's going to be, now you're thinking in terms of Galois theory. And that, yes, that is where we're headed. No, these are all good thoughts I'm hearing you all throw around. Shows you all are kind of thinking in terms of the direction I'm trying to lead you. Falling into all of my traps.
We're also eating up your behemoth proof time.
Alright, you wanna start proving this?
Yeah.
Oh, true.
Okay, 15 minutes. We are not gonna have enough time to prove this, but we can start proving it.
I'm glad.
Oh yeah, I forgot to actually bring that back.
Don't forget the class is over.
Shut up. I've learned my lesson there. You can't fool me. So let's see how much this.
I fooled you into calling it the culture group several times.
That's less fool me and more just like me making a Freudian slip. That's not like actually fooling me. All right, let's prove. So basically, we're going to break this up into two cases. Our proof is going to be, suppose there exists some polynomial for which alpha is a root, and suppose there does not exist some polynomial for which alpha is a root. If there exists no polynomial over k for which alpha is a root, if there's no polynomial, then we'll prove we're in case 1. And if there is a polynomial for which alpha is a root, then we'll show that we're in case 2. So that's how we're going to approach this. So first of all, for part 1, we're going to suppose no non-zero. You always have to exclude the 0 polynomial because everything's always a root of that. F in the polynomial ring over k satisfies f of alpha equals 0. So start with assuming essentially alpha is transcendental over k is how we're going to define it in the next packet. And then we need to find some isomorphism from between these two rings. So I'm going to define some map phi going from k of x to the field k of alpha. We know everything in this field has the form f of x divided by g of x for some f of x and g of x polynomials in k. So here's the question. How could we take a quotient of polynomials over k and somehow get something that's of the form that's in K of alpha. Lincoln?
Just set x equal to alpha.
So in other words, just evaluate at alpha.
Yeah.
That's how we're going to do it.
Nice.
That's pretty.
Well, I'll leave it as an exercise to you all. Maybe I'll put it on the homework. Maybe I won't. Phi is a homomorphism. Ring homomorphism, specifically. That one's fairly easy. Phi is onto is also fairly straightforward. Why is phi onto? Because we know every element in K of alpha has to look something like this from that theorem on the previous page. The little theorem where I said K of S is the quotients of finite linear combinations of finite products of elements of S. That's a fancy way of saying this in this case. So we know every element in K of alpha can be expressed in this way somehow. Probably say f of x, g of x. Elements of x. The interesting one comes from showing phi is 1 to 1. No, this is not a fit. This is not time for fit. There are no quotient rings happening, even though it kind of looks like it. I'll say our.
Wait, are they in K? Oh wait, no, yeah, never mind. Just
These are easy to show.
I see, yeah.
So let's suppose, let's show phi is 1 to 1. Sounds a little bit tricky. So we're going to suppose phi of f of x over g of x equals phi of h of x over k of x. For some f, g, h, k, and this thing.
In kx.
Yes.
Kx and kx.
Maybe I shouldn't use k. Let's use p. Get some Harry Potter in here.
Health
Right.
points.
Health points.
Hewlett Packard.
Yeah, that's what I
Do
said.
it.
Oh, we were talking about Cthulhu.
So that tells us what? Well, f of alpha over g of alpha is equal to h of alpha over p of alpha. And then if we do a little bit of crisscross applesauce,
I love that.
we're going to get f of alpha p of alpha minus g of alpha h of alpha is equal to 0.
Ah,
Ah,
I have thoughts.
what are your thoughts, Emily Rose?
If, well, if f of alpha, wait, isn't there a way that that could fall out so that it would, alpha would have to end up being a root of some of those functions?
Yeah, well, f is a root of fp minus gh. Alpha is a root of fp minus gh, which is some polynomial over k.
Isn't it also important to note that G nor P can be 0?
Why can't g or p be 0?
Oh, because we just,
Oh, well, yeah.
we divided.
I mean, sure. It does. That doesn't end up being important, but
Oh,
yes.
okay.
But it is true. G and P can't be
Okay.
identical to 0.
Okay.
But fp minus gh is going to be a polynomial in k of x for which alpha is a root. But we said that f is polynomial, but no polynomial in here should have alpha as a root,
Except for the zero polynomial.
except for the 0 polynomial. That's a contradiction if we're assuming not 0. Which means f of x, p of x, minus g of x, h of x, has to be the 0 polynomial by our initial assumption. Which means, do a little bit of reverse crisscross applesauce. F of x over g of x has to be the same equal to h of x over p of x. I.e. v is 1 to 1. And that's our proof of part 1. That if at least no non-zero polynomial f has alpha as a root, then this is isomorphic to that.
So, wait, is that identical to f of x over g of x equals, because there's the 3 lines up there for the 0, so is it 3 lines in the next?
I mean, they're the same polynomial. I'm just being careful to say equals. If you just say equals 0, it makes it sound like, oh, that's an equation you can solve for x for a particular FTPH. We're saying, no, that's not an equation you want to solve for x. We're saying that is literally just a polynomial that simplifies down to 0 no matter what x is.
Yeah, so that's just saying that those two are equal no matter what x is.
Correct.
So,
Yeah, I mean,
That's
does that make you feel better?
yes.
Okay. F of x over g of x is the same polynomial, or is the same rational form, I should say, as h of x over p of x. Rational form meaning quotient of polynomials. So there we go. If if alpha can't be a root of anything, non-trivial, then it is isomorphic to notice that we relied on this no non-zero f satisfying this, because otherwise the function we would have made would still be an onto homomorphism, but it would not be 1-to-1. So this condition was necessary in order to be able to get an isomorphism here, rather than just an onto homomorphism. Any questions or comments about that? All right, that's one of the things we need to prove down. Well, 3 of them, I guess, if you include homomorphism and onto, which I said are easy. So step 2, we're going to look at the opposite case, where now there is a non-zero f with alpha as a root. What?
Have to switch pages.
You've put plenty of pages.
Oh yes, I gave you like 3 pages for this for a reason, because you're going to need them. Well, maybe Rose will only use 2, but...
I might only use 2, but I will definitely need 2.
Okay, so here's part 2. Part 2 is longer than part 1. We're going to now suppose
What?
some non-zero f of x polynomial over k satisfies f of alpha equals 0. The opposite of the condition we assumed or the negation of the condition we assumed at the start of part 1, at the part of start 1. And we're just gonna go right for the jugular on this one. We're gonna define m of x to just be some polynomial among all of them that satisfy this condition that's of minimal degree. So we're gonna let m of x, the polynomial here, have minimal degree among all such polynomials.
As in the f of x.
Yeah, among all the polynomials in here that have alpha as a root. Pick whichever one of these polynomials happens to have minimal degree. We're going to let that be our m of x. Look at.
And should we also define it as monic, since we could just divide?
Well, yeah, I'm about to say technically n doesn't have to be monic from this, but we could just, without loss of generality, say it's monic, because if it isn't, then just divide the whole thing by its leading coefficient. Without loss of generality, m is monic, meaning leading coefficient is 1, because if it's not monic, else just take m divided by leading coefficient of them. What? What's that, James?
Oh, I was just joking that if this was
Making
coding,
fun of
then we would just say m is equal to m over the leading coefficient of n. Just
Yeah.
like you wrote right there.
Well, I mean, just taking something a minimal degree doesn't itself guarantee monicness,
Yeah.
but you can guarantee monicness by if you take something a minimal degree and it happens to not be monic, make it monic. Jonathan? Okay. So now we have our m of x. We know it's monic. We don't know it's unique. We don't know it's irreducible. Well, proving it's unique is not hard. But we don't know it's irreducible, and we have to show all these three conditions. So we're going to do this in a specific order. We're first of all going to prove this one. Then we're going to go back and talk about trying to combine unique and irreducible and somehow got yawn out of it. We're going to prove this. Then we're going to prove unique and irreducible. Then we're going to prove this. Then we're going to prove this. Sound good? All right. Yeah, I think we can prove this one and call it quits. So, subcondition number 1. We have an if and only if to prove. Well, one direction of the if and only if is pretty straightforward. Which direction?
Backwards?
Yeah, backwards direction. If m divides f, then the fact that m of alpha equals 0 guarantees that f of alpha equals 0.
The other direction is also fairly straightforward, right? Because we said that I was.
Hold your horses. If m divides f, then m of alpha equals 0 immediately implies f of alpha equals 0. And Eleanor, you think the forward direction of this is also pretty straightforward?
Yes.
How would you do that?
Because we defined m of x as being the minimal degree of all polynomials.
Yeah.
So
Why does that mean it has to divide all other polynomials doing it? It has to have smaller degree than all other polynomials f that satisfy that, but that doesn't mean necessarily it divides, does it? How do we... We're going to have to pull an old tool out of our tool bag on this one. How do we show that if f of alpha equals 0, that m has to be a divisor of that? How can we show, in other words, that if we were to try and take, I don't know, f divided by m, we would get a remainder of 0? I'm going to go with Euclidean algorithm because that's what kind of we've been calling it, but yes, exactly. Yeah, we're going to do some Euclidean algorithm for the forward direction. So, forward direction, we're going to suppose f of alpha equals 0, and then say for some q of x and r of x in the polynomials here. Keep in mind, we've proven that a ring of polynomials over any field is a Euclidean domain, so we can Euclidean algorithm it up. So for some this, we know f of x equals q of x, m of x, plus r of x.
Why is it in square brackets?
Because these are just polynomials, because we know for some polynomials specifically.
Oh,
because if it's when they're dividing, we use the.
oh yeah, I just.
Yeah.
Wait, which
Because here, when we're saying m divides f, we mean m divides f in this ring right
Yeah.
here. Not in the ring of rational forms, because there everything divides everything.
Mhm.
Every non-zero at least.
Which thing do we know is a Euclidean?
What?
Which thing do we know is a Euclidean? K or K.
Yeah, polynomial ring over k. That was something. That was one of these big results we proved back in like a couple weeks ago. For where the degree of r is strictly smaller than the degree of m. Well, then if we take r of alpha, we're going to get f of alpha minus q of alpha, m of alpha, which is 0 minus 0 equals 0. R of alpha is 0, but an R is a polynomial of degree less than m. And m is the smallest non-zero, is the non-zero polynomial with the smallest degree that has alpha as a root. What does that allow us to say about R?
It's the zero polynomial.
It says that R of x is the zero polynomial by minimality of the degree of m. And then from there, we can very quickly, sorry I'm going a little fast here, but we're out of time and I just want to finish this one part real quick. From there, the fact that we know R of x is 0 tells us that f of x can be written as some multiple of m of x, which in turn tells us that m defines. Okay, we'll stop there for today. So when we come back next time, we need to still prove parts 2, 3, irreducible, and unique. Which shouldn't take us that long, because again, none of these parts I think are that bad. There's just kind of a lot of them. And then from there, we'll start playing around with more examples of how do you actually find minimal polynomials.
Sorry, so how does the minimality of degree n tell us that R of x is identical to 0?
Well, I would tell you, but Parker's deciding to block the way. Stop the video.